And it's unfortunately the note that you're coming off the Space Center Boulevard, you're coming down that long street in the back, and turn at the water tower, turn south of the water. Okay. And then if you're going south on the water tower line, the first building, it's a parking lot, is building 36. That's where the land. So you just pull on the parking lot, and I'll be there.
No, I'm familiar with it.
Okay. So I haven't found boyfriend yet. I just got back there. So try to encourage him. Get there over the
Yeah.
That sounds good.
Yeah, so it's different lines of evidence. It definitely sounds
There's another question. Ionization states in gas. Ionization states you can make lightning adjustments between both locations. So you can get incredibly charged up gas and those things. So it doesn't surprise me that there's a ton of the problem that we're looking at is kind of like so we have good gas yeah, so that's wants to try to settle down a bit. Okay. Gas storage is higher than the setup of gas. Comparing the sun for plant.
All right, so I probably knew I shouldn't have said we were doing great on time because this is where everybody won't be back, but we're going to go ahead and start in a few moments here. I'll give everybody 30 seconds.
So we're trying to figure out how to use the planets.
You know how to pronounce that. Scott, how do you pronounce your last name again? Sevchek. Yeah.
yeah.
Okay, while we're waiting, we'll get started in just a minute. Just remind folks that are out there in the virtual world that they can post their questions and comments on Twitter to #ProtectPlanet. And we appreciate the folks that are participating from a remote location, and love to hear your input and comments either now or during the discussion period later after the finishing of the presentations or tomorrow morning. And again, I'll mention this at the end, but we're going to have a session. We'll have a short discussion this afternoon, and then from 8 a.m. to 10 a.m. and we'll have a follow-up discussion and synthesis period. So with that, I think we've got most people back in the room. Our next presenter is Scott Sevchek. He's the president of Prospect Dynamics. Scott has worked as an engineer and a program manager in missile defense, space launch, and aircraft systems for Lockheed Martin and United Technologies. And welcome, Scott.
Good afternoon. As I said, I'm Scott Sevchek. And today I will discuss the alternate method of saving condition. And really that's what I want to talk about is architect And just as a note of context, coming at this from the standpoint of Prospect Dynamics as a company that's working to develop technologies to support asteroid mining, there's a little bit of a different mindset that we came into this with. We're looking at technologies that we're developing that have applicability in one area and how they might be applicable elsewhere, planetary defense being one of those concepts. So getting to a new architecture, we focused on 3 areas: scalability, flexibility, and cost. For me, scalability is significant because it means time. The more we are able to scale the system on demand, the less time we require in order to bring about the effect that we're looking for. So the ideal system in this sense would have all of the equipment, all of the components of the architecture on the shelf, and when a threat is determined, be able to configure to scale the impulse required or the capabilities required for the mission. Flexibility, similarly, is about having options. It's about being able to approach an architecture not as a point design, but without a priori threat information in developing a general system that uses 90 to 95% of the same equipment regardless of what you're doing, but has that element of configurability or flexibility that can allow you to address potentially a range of different options or a range of different threats. And finally, cost being the third option. Like it or not, there isn't really a business case for saving the planet. So that brings us to working within funding that is available and funding that may be available for other related applications, and looking at how do you leverage that funding to develop the pieces of the architecture that would be required for a planetary defense mission. Where that led us was the multiple attached vehicle concept. So we focus essentially from the vicinity of the asteroid on down. In this concept, the large vehicle that is going out to the asteroid serves as a truck to deliver a fleet of microsatellites. Once on site, these microsatellites deploy individually, find a location on the asteroid, and attach to it. So you end up with essentially a mesh network of satellites on the surface of the asteroid. This provides you a ability to use this distributed architecture of sensors across the surface of the asteroid to characterize and understand the asteroid more fully than you would from either remotely or contacting at a single point. It also provides you with the flexibility that I discussed on the previous slide. So under a reference concept, each one of these vehicles would carry additional propulsion with it. Then you have thrust points covering the surface of the asteroid. And you can use that thrust in a number of different ways to bring about a slow push or a detumble or various other ways of affecting the asteroid. You wouldn't have to just bring propulsion, though. You could configure these individual microsatellites such that they are carrying drilling equipment or carrying explosives. So if you wanted to look at explosive fragmentation, either in a radical fashion or in more focused fashion, you could potentially bring with microsatellites that drill into the asteroid in different areas, strategically weakening it, and then using explosives placed at key locations to detonate that and separate off a large chunk of the asteroid or a smaller piece of the asteroid, depending on what the approach you're looking at is. So in looking at this as an architecture overall, the left side of the screen is exactly the same 100% of the time. You have a ground communication element, a launch vehicle element, and this transit and deployment vehicle element, which all of these are technologies that either exist or are currently in development in the case of the SLS. What I would envision in the middle as that truck would be similar to the geosynchronous base satellites we've been discussing earlier today as a baseline concept. So technology that exists being adapted to the purpose of delivering multiple smaller vehicles to the site of the asteroid. And that is really one of the key pieces of scalability within the architecture, because you don't need to predetermine how many satellites or microsats you would necessarily bring with. You could build this in a scalable fashion, such that you bring additional rings or additional components, deployment components for these vehicles. And that really could scale to the point of affecting the launch system as well. If you had a need, the Hollywood doomsday scenario where you needed to bring a lot of impulse in a short period of time, you could scale to the point where you deliver to orbit, to low Earth orbit, on one fleet of micro-attached vehicles via one launch, and this transit deployment vehicle aboard another launch, rendezvous them in orbit, and then your truck becomes a train pulling a large number of microsatellites and their deployment mechanisms with it. The right side of the screen is about the mission package. It's about what you bring with so that you can achieve your mission objective on site. So, as I mentioned, the slow push concept would imply that these are largely propulsive vehicles that you're bringing with, or have a propulsive payload with them. Or you can bring in a mix. You can bring in components like ground penetrating radar or other sensors, special sensors that you want to carry with for a better understanding of the body. Drills, explosives, as I mentioned, or something like a transponder with additional long-range communication, so that whatever you're doing on this asteroid, you can then leave this behind and use it over a long period of time. And I said the left side of that screen was existing technology or technology already in development. When it comes down to the microsatellite, the large portion of that is already in existence as well. The bottom right corner of the screen, don't get hung up on that. It would not look anything like that. It's meant to be a notional concept of what the fundamental architecture is. The bulk of the microsatellite vehicle is just that. It's a space vehicle. It contains all of the propulsion, comms, data handling, everything you need for that space vehicle to operate. Then there are two other pieces. One, since you want to attach to the asteroid, an attachment device. The other, a modular payload. So you start with an interface, and then you bring that ability to bring on a payload as we had discussed for the various mission packages. The way that works out now is the bulk of that core bus is something that you can buy online right now. Between CubeSat technology and microsatellite technology, the bulk of this vehicle you could put together today. Key pieces remaining in development are this attach mechanism, which is where we're focusing, the integration, the software for coordinating the swarm of microsatellites and the interaction between them while on the surface, as well as that payload interface and the payloads that could be adapted to it. Many of those would be to reuse existing propulsion technologies or existing other technologies and packaging them for this application, this interface. Where that gets me to is the least mature part of this architecture is something that we could demonstrate in low Earth orbit, not go to an asteroid to demonstrate. And that is the integrated microsatellite with an attached capability. So how I see this working is launching maybe a handful of these microsatellites, CubeSat class microsatellite, into low Earth orbit. And then we use the closest analog in low Earth orbit to an asteroid, which would be a piece of space debris. Something that's tumbling, uncontrolled, not designed to be mated with. Take these CubeSats, demonstrate the ability to find locations and attach to that, then use that to characterize the motion of the asteroid, or asteroid analog in this case, the space debris, and then affect the orbit of that space debris. If you are altering the orbit, you can think of it as a proof of concept for certain capabilities with respect to on-orbit servicing. If you are using this as a controlled deorbit of that piece of space debris, not only have you demonstrated your capabilities for planetary defense and the attachment itself, but you've also now demonstrated a rather low-cost, straightforward approach to mitigating large pieces of space debris. So this is the demonstration that really matures the micro-attached vehicle component of this. And then if you wanted to tie back to the ARM mission with something like this, the opportunity there would be to bring along a handful again of these microsatellites to deploy on site at the asteroid and use them in that asteroid context, in that relevant environment to in place a transponder, to demonstrate the ability to attach, potentially to demonstrate the effect of drilling or some other concept on the asteroid. So the focus here is a low Earth orbit demonstration, but it does open up the possibility to a demonstration in coordination with the asteroid redirection mission. So going back to those key elements, the scalability within this system really comes in two dimensions. First, the number of microsatellites, as well as the capability you put in those individual payloads. Nothing in this architecture is predetermined. You could take a chemical propulsive payload, an electrical propulsive payload, whatever you want to do. You have opportunities for flexibility within this architecture. And that buys us time. Second, flexibility. This allows us to approach the problem of planetary defense in multiple ways, through a slow push, through fragmentation. So it spans a portion of the chart that Bongwei presented earlier, where depending on the time you have available, you may need to look at different options. And finally, cost. As I went through, the bulk of the technology here is already developed, and we're talking about a repurposing of technology that's already in existence. Also, as has been pointed out a little earlier, that there are single point failures in a lot of the concepts that have been described. This opens up that tolerance. You have a lot of microsatellites, and you could potentially bring more microsatellites that you need for the baseline mission. And in doing so, you could lower the cost, lower the necessary quality standards, because you have dozens or hundreds of these that most need to work, rather than a single device that has to work perfectly. So benefits both in terms of development cost and recurring cost from this standpoint. Also timeline. With the fact that so much of this technology is already in existence, the pacing item is really the development of the attach mechanism and the demonstration of that capability. Everything else is a matter of configuration. I'd be happy to take any questions.
Any questions?
You said at some point CubeSats. Are these actually CubeSat size? Is that the idea here?
So that is something that, as
Is it-
early in the architecture as we are, we have some flexibility with.
And-
What I would envision for the near-term demonstration would be CubeSat class. When we put this up to alter the trajectory of a piece of space debris, yes, I think they'd be CubeSat class. On an asteroid, I think they might be a little bit larger.
And so what sort of propulsion would they actually have?
So there is nothing that is necessarily determined at this point. Each of the microsatellites themselves would likely have a chemical attitude and divert control system for attitude, positioning, and rendezvous with the asteroid, since they're being delivered to the vicinity of the asteroid by the truck, by the transit deployment vehicle. Then you would be bringing a payload along, and the payload that would bring about the divert of the asteroid, those are something that we can specify in a number of different ways depending on what we want to do with it. You could bring a propulsive payload that is chemical, and then potentially you're pulsing as the asteroid rotates. You don't bother with detumbling, and when one CubeSat is aligned with the vector you want to push, it pulses. When another one comes by, it pulses. Or you have a distribution of solar electric propulsion payloads. So this architecture really allows that flexibility and doesn't need to answer that question.
Yeah, all that sounds like to me just, I have to say, a lot to put in a CubeSat. I mean, to have an attitude control system and, I mean, the payload, yeah, sure, you have some sort of payload and you get to specify that, but it just seems like you're talking about a CubeSat that, the ones I've seen are pretty simple. They don't have attitude control or anything, but it's got to get from the bus to the surface of the body. It's got to have some ability to thrust. It's got to have some ability to control its attitude. It's got to have, I mean, it seems like that's a lot to put in something that's...
There is a lot going on with 3U CubeSats. There is quite a bit of functionality that's being packed into those packages now.
Okay.
something to keep in mind as you, if you're going to place multiple of these assets on the surface, is the thermal problem. You're going to have thermal cycling problems as well as very cold periods that are probably going to require heat in some form, which is going to require then some larger solar arrays depending on the asteroid's distance and so forth. Also, you mentioned that you're working on developing an anchoring system. Can you say anything about that?
Okay. As to the first part of your question, the nice thing about working on this scale is each one, and working with multiples, is each piece of equipment doesn't need to carry all of the functionality. There's the benefit of multiple devices. So if you need devices that if things need to shut down for a portion, if they can only operate in certain ranges, that's fine, because something else is carrying the load and doing the work at that period of time. So by having the broader architecture, you're able to mitigate some of the concerns, but certainly thermal issues, a lot of the other issues you mentioned, have their start in some of the CubeSat work that's being done now and would require extension for deep space operation. But I think they're not insurmountable problems.
Okay, thank you, Scott. Move on to our next speaker.
Okay, our next speaker is Bob Bueller. He's a senior technologist for advanced projects development at NASA Kennedy Space Center, and he is in the engineering and technology directorate. He's also the co-founder of the KSC Granular Mechanics and Regolith Operations Lab. So Rob, whenever you're ready.
Okay, can you hear me? Are we live?
We're live.
We're on the internet.
We are
Okay.
on the internet.
Okay, just checking. So, good afternoon. I'd like to acknowledge my co-investigators, Dr. Phil Metzger, Dr. Laurent Sabile, and Dr. Jim Montavani. And what we'd like to talk about today is the utilization of surface material for asteroid deflection, and by that we mean regolith. And regolith and any other kind of resources that you might find on a NEO or an EIA. And of course, we're just talking about the NEOs that are Earth crossing. So it's these two classes we're showing here, surrounded by the dotted line. And the premise is that if you can give a delta velocity to the object, then you can it can cause a very small change in orbit, but that small change in orbit is enough to miss the Earth. So what we're talking about here essentially is providing delta V, and that is provided by an exchange of momentum with the asteroid via ejection of surface material. Of course, that has to happen at appropriate times in the rotation period. And this just follows the basic principle of a rocket. It's a device that can apply acceleration to itself, a thrust, by expelling part of its mass with high speed and move due to the conservation of momentum. And then what we're showing here is Tsiolkovsky's rocket equation, and that's what we used to do some just very preliminary calculations to show. We were wondering if this was feasible or not. And there are two options basically that we've identified. Option one is you eject regolith so that the mass that you're using is the regolith, or you could eject boulders, and that would form the exchange of momentum. There has been previous work on this. Olds and Charanaya had a NIAC Phase 1 contract from NASA in 2004 where they looked at a similar kind of idea. Also, Dr. Sabile and Dr. Montavani, who are in our lab, they also received a NIAC Phase 1 contract in 2012, and they're about to propose for a Phase 2 contract, and we'd like to roll some of this thinking into that Phase 2 proposal and take this work a little bit further. And so the picture you see on the right there is these ejection of these volatiles. If there are volatiles on these NEOs, then if you heat up the volatiles, you can have sublimation of gases and focus that through a nozzle and then get a thrust. And then on the other one, the ejection of regolith or boulders, that could be via a mass driver or a catapult, some kind of device to eject the regolith. So if you use that rocket equation and you do this is just a case study. It's not defined exactly what we need. We just did it to get a ballpark figure. We picked a 400-meter diameter object with various mission durations. We said it had to achieve delta V of 1 meter per second, which may be large. We also said that gas-solid material is ejected at a velocity of 32 meters per second. We assumed that the asteroid has a density of 2,000 kilograms per meter cubed. So if you just run the rocket equation, you get this curve here, and it shows you that the ejected mass rate on the vertical scale here, it's rather high. These numbers are the kilograms per second. So then this becomes sort of asymptotic, and so you get to 66 kilograms per second, and that was the kind of metric we were looking for, because in our lab we specialize in situ resource utilization and specifically in robotic excavation. And so we were trying to see, is it feasible to send a robotic excavator to an asteroid with some kind of energy source and a mass driver, and then use the in situ material as a propellant to form an exchange of momentum. And so it turns out that that is possible if you look at these numbers. The attractive thing about this concept versus the other concepts is that the mass you have to transport from Earth to the asteroid is small, because the exchange of momentum is provided with the mass that you find in situ. So that is the attraction of this concept. However, the trade-off is that even though it looks attractive from a mass transportation and delta V from Earth point of view, there is a level of technology assumed that we don't have today and would need to be developed. And also there's a level of reliability. If you're really doing this for planetary defense, would you rely on these robots to perform this kind of orbital trajectory change? So we think it is possible, but it would require some technology development. So you need a mass driver, a catapult, or some kind of other throwing or pushing device. People have proposed electrostatic devices, electromagnetic devices, all kinds of things, but the key is it has to be low mass and reliable. Mining technology, we are developing robotic excavators today across the agency and private industry. I have a competition called the Robotic Mining Competition, NASA Robotic Mining Competition. We have 50 universities come to Kennedy Space Center every year with a robotic mining machine. They dig in a simulated lunar regolith of Black Point 1 crushed basalt. So we have 50 university teams every year working on this problem. And I think it could be done. Now the next thing you need is solar cells or nuclear plant to provide energy to the above items. And that is a caveat on this whole thing. You do need the energy. But one other attractive thing about this is several of the presenters at this workshop have said that there's a very large degree of uncertainty on what the size of the asteroid is before you ever get there, just because of the remote sensing technologies we have. So you might get there and it might be much, much bigger than you thought. And so your system has to be flexible to accommodate that. So with this kind of a system, which uses the in situ materials, you can do that. You can be flexible in your concept of operations. And so that's when I talk about control knobs, that's what I mean. Is if you have a situation where you arrive and you don't have what you expected, then you can turn your control knobs and maybe still solve the problem. And in our studies of this technology, we're going to need to look at all these control knobs and see if this is possible. But so the control knobs that I've listed here, and there are probably some more, is you can increase the ejection velocity, then you need less regolith. You can increase the duration of the total ejection, then you have less regolith ejected per day. Decrease the period of rotation, because you can only fling it off at a certain point in the rotation to be effective in either increasing or decreasing the velocity of your object. And you might, if you require less delta V, we assumed 1 meter per second delta V. If it takes less than that, that's less regolith. Also, the volatiles could be used if we find volatiles. So some of the negatives are that excavation is high but not impossible for robotic excavators. We have to look at this delta V. We don't really understand what the delta V is. Maybe some of you can help us with that, because there are other people studying that. One interesting idea was thermal fracking. You know, fracking is such a big subject these days. What if we did thermal fracking on an asteroid and we broke up large chunks of it? So because we're talking about digging small little scoops, what if we broke up large pieces of the asteroid? What if we scored the asteroid and then broke off a chunk? So there's that kind of thinking too. And we're studying methods for mining the regolith. So this chart has showed up in many instantiations over the last day or two. And what's interesting about this is the spin rate and how there are no asteroids above the 2.2 period. And so Dr. Laurent Sibille came up with this idea of everybody's been talking about despinning an asteroid. What we'd like to do is spin it up. And so what we'll do is we'll take the same technology of regolith ejection or volatiles sublimation, and you place it in the right spot on the asteroid, and you spin that asteroid up until it hits that velocity where in the diagram below it actually disintegrates and fractures. And so this is a kind of a inverse thinking, and but I think it's worth some study. Now there are some negatives in that you have a debris field now, which you can't necessarily predict what size each chunk will be when it breaks up. But in theory, you could have a good solution there. And so Laurent has run some numbers here, and they're shown on the chart. But the basic idea is if you go to this chart, and if you spin it up, then you get into this place where there are no asteroids, large asteroids, because they've all disintegrated. If you're down in this region, then you can't do it. Then you have to use the other method that I talked about, which is momentum exchange with regolith. So in conclusion, our very quick preliminary look at this indicates that asteroid deflection is possible by ejecting in situ surface material through propulsion devices. And ISRU options allow operations changes to mitigate if the asteroid breaks or it's into pieces or if it's larger than expected. It gives you an operational flexibility because you have this equipment there, this robotic equipment, and you can change your game plan in the middle of the game. Regolith, boulder, mining, mass driver, and power equipment must be transported to the asteroid and operated reliably. So there's a caveat there that if this equipment is not reliable, then it's not a good architecture. And increasing the spin rates may cause slow rotators to break apart by rotational fissure. And there are some papers out of the University of Colorado, I believe one of the authors might even be in the room here, that talk about rotational fissure and have studied this at the University of Colorado. So it's a valid concept. And that's all I have. Thanks for your attention.
Okay. Thank you. Do we have any questions in the room? Any questions online?
Just real quick, Rob, just maybe a comment. I mean, it's spinning up an asteroid to fission it. Question is, does it just reaccrete when you're done? So, you know, I think there's a lot more detail if you want to think of that as an approach, because you got to maintain that spinning beyond that fission point. So, just a comment.
Yeah, it's just this idea of going the opposite way.
Sure. No.
And maybe doing something with that. We haven't put a whole lot of thought into it, but we're at the brainstorming level.
Yeah, absolutely. Okay, thanks. All right, our next speaker is Rob Adams. Dr. Adams has 18 years of experience in space program, conducting studies in advanced propulsion, planetary defense against asteroids, and mission design. And he's from Marshall Space Flight Center, where he's worked for the past 13 years. So welcome, Rob, and as soon as you're mic'd up,
Good.
you can start. Thanks.
All right. Thanks, Dan. Okay, so today I'm going to talk about the solar collector option. So just in case you guys aren't familiar with the idea, Here's a diagram of it right here, an old sketch that I did about a decade ago, actually. The solar collector is actually an offshoot of the solar sail. The solar sail suffers in that the sail has to face the sun to be illuminated, but if it does, then the thrust vector from the momentum exchange of the photon bouncing off the solar sail make the sail want to go radially out, which is actually not very helpful when you're trying to change your trajectory. You tend to want to accelerate along your flight vector, so you tend to fly your solar sail angled relative to the sun. So somebody a while ago proposed, well, hey, why don't we do a solar collector where we shape the sail into a parabolic dish and have a secondary collector, and so now we still get that radial force from the sun, but we also get this tangential component, and so we can get a better direction of force and be able to use the solar collector to go where we want to go. The problem with that is that in doing this, we reduce the total effective area being illuminated by the sun, because we're not, a flat shape anymore. Now we're a parabola, and so this concept kind of fell out of vogue in terms of just a straight propulsion device. However, it kind of came back back in '94, if you will, by Milosh, presenting it as a way to maneuver asteroids. And so there are a lot of operational capabilities here that I think are unique. I mean, we don't have to touch the asteroid. We're able to handle an asteroid tumbling on multiple vectors, if you will. We can use the system to actually maneuver ourselves to the asteroid and station keep while we're there as well. Here, Milosh has a station keeping propulsion system, but really that's not necessary. You can just use the solar cell itself and have times where you're illuminating the asteroid and times where you're maneuvering back into position to illuminate the asteroid again. So lots of positive operational concepts. Of course, from the earlier talk about messing up the crust, we're going to mess the crust up a great deal after this. So, you can't have everything. So the question is, well, how effective is it in actually pushing an asteroid around? And so this RASC study, so this was RASC was run out of Langley back in the, early last decade. And Dan and I had sister projects, and this is the one that I was leading here. And so this one here, we were looking at, a large variety of asteroids. At this point, we had not retired the 1 kilometer risk. It was back in 2002, so we were actually considering very large as well as very small asteroids. Now, for the mission of, defending the Earth and all that, we generally need to produce about, somewhere in this category right here, 0.1 to 0.01 meters per second to push an asteroid out of the way, assuming we have about at least 2 years lead time. So with that, you can see that the solar collector, or this solar collector that was 100 meters in diameter, was barely effective at 1 kilometer. I mean, you would have to illuminate, if you needed the lower end of the delta V, you would need about 100 days of illumination, which, doesn't sound too tough here, but boy, when you get out here and you need that, 10 centimeters of, 100 centimeters of delta V, and you've got to operate for 3 years continuously, that's starting to get hard to swallow. The other mission that's important that we should talk about here is right in this range right here, where we're trying to produce, that 500 meters to 1,000 meters per second, where we're going to do the asteroid redirect mission, taking that 10-meter asteroid and pushing it around the solar system and sticking it in its own slot here in the Earth-Moon system. And so, again, here you can see that our concept can handle, that 10-meter asteroid very well with a couple orders of magnitude to spare. Now, the model here was a very early model, and we were designing the system so that it operated mainly around the 500 nanometers that is the center line of the solar spectra, and we were assuming pretty much everything made it to the asteroid. And that's a pretty aggressive assumption. So, but my point here is that we could accept 1 to 2 orders of magnitude of operational inefficiency. So we could go down to 10% efficiency instead of 100%, and still be able to do that redirect mission, and we could still handle asteroids in the not up to a kilometer, but definitely hundreds of meters to do planetary defense. Okay, so a few years later, we took on another project, and here we were looking at using the solar collector as one of several options that would be launched on the AIISW vehicle. So that's a predecessor to the SLS here. And so we came up with this mission concept where we had this LOX hydrogen kick stage that would kick us into out of Earth's orbit. And it turned out this thing ended up being almost identical to a Centaur upper stage, so in terms of mass and performance requirements. Then we had this cradle system here, and then we could put 6 bullets, is what we called it. And we had a kinetic interceptor, a nuclear interceptor, and the solar collector option all hanging off of this cradle. And so each one of these bullets, if you will, would detach from the cradle. The cradle would continue to fly towards the target asteroid, and then the bullets would accelerate, for the nuclear or the kinetic option, or deploy for the solar option and start to operate on the asteroid. And so here is the solar collector in its inflated state. And so, this is a little bit better drawing than my hand drawing before. Here we were looking at 50-meter solar collectors, and you can kind of get an idea for the dimensions of the solar collector versus the secondary mirror. Also, we controlled our solar collector with tip vanes that also doubled as our avionics suite. So you can imagine these as highly reflective on one side, but solar arrays on the other. And each one of these were independent avionics modules that could run the solar collector independently. So I think I kind of said all this. One of the big concerns we had back in 2007 when we did the study was trying to figure out how to unfold and fold something more complex than a solar sail. But after 2 days of listening to people talk today about unfolding inflatable claws and whatnot, I feel a lot better. One of the major design issues is the secondary collector. You can imagine the amount of power that's being focused onto the secondary. And so what we have to achieve here is a very high reflectivity on the front so that we can limit the heat absorption of that secondary. And then we have to use a fairly, I wouldn't say exotic, but we're having to use an advanced heat pipe rejection system to keep it cooled on the back. Now we can always alleviate this problem by making the mirror bigger, but of course that reduces our ability to focus on the asteroid. And then I've already mentioned the tip vanes. Okay, so our mass breakout is shown here, and like I said, each one of our bullets we targeted at 1,500 kilograms. And so you can see here we have a pretty healthy growth margin here, and our sail aerial density, which is a performance parameter for solar sails, works out to be about 25 grams per square meter, which is pretty conservative. We have already achieved better numbers than that with the solar sails that are being designed today. So this concept here, we started looking at making a little bit better assumptions on how much power was actually going to make it to the asteroid. And I think here we used a 50% power from the solar collector to the actual asteroid. And here we're also focusing on asteroids between 100 meters and 1 kilometer. And so we were able to calculate accelerations. I mean, we've seen that with several presentations today. At the same time, this was 2007, so Apophis was the poster child for planetary defense. And so we modified Apophis's trajectory so that it would hit the planet in 2029, just on the computer, don't worry. So we actually wrote a trajectory program to just kind of integrate the equations of motion and back out what acceleration would be required as a function of the time before impact. Previous studies, ours and a number of others, have shown accelerating or decelerating along the velocity vector tends to be the best way to perturb an incoming asteroid's orbit. So with this, we have an acceleration versus time before impact, and we have an acceleration versus asteroid diameter, so we can kind of combine the two here. And so for a given acceleration, we can read what diameter asteroid we can defend against at with a given warning time. And so, oh, okay. And I thought you were stopping for a question. So this graph right here is definitely showing that if we look at here, giving ourselves 1 to 2 years warning time, we can still hit asteroids at 300 meters. And this is, remember, a 50-meter collector, where the last one was 100. So this is 1/4 the size, and we're still able to handle a pretty decent-sized asteroid. And that's assuming one at a time. If we launch 6 of them at a time, then we've got 6 times the capability, assuming that they can all interact with the asteroid. Or we could have them come in one after the other. After one is damaged or otherwise has become ineffective, we can push that one to the side and have another one come in behind it. So there are several issues that we need to address. One is there's a coupling between how close the collector has to be to the asteroid. We want to be close to get as much of the sun's radiant energy onto the asteroid, but we don't want to be close because the ejecta from the asteroid is going to impinge on our secondary and our primary. So, and that is not a well understood mechanism here. Now we have this solar thermal facility that Harold's not, oh there he is, Harold Garish and some of the other folks at Marshall worked on, and it's a really nice facility, and we could, right now put some regolith in this vacuum chamber right here and start testing, what our ejecta rates would be, and get an understanding of that problem. Also, we need to have a collector that's large enough, that is intense enough, that we can heat parts of the regolith and get it to vaporize before all of that heat dissipates back into the asteroid. Now here's where a rubble pile actually works in our favor, because we would expect with that much void we would have less of a heat dissipation through the asteroid. But that's something else that would need to be analyzed. I'll skip this because I think all day we've seen people talk about all the experiments on inflatable mechanisms. I think that's well understood or well along its way, and there's some capabilities at Marshall and other places where this has been done. And then this is just generally showing, hey, we're up to 20-meter solar sails that have flown, the Japanese, the 10-meter antenna that was flown on 77, the things that we've done on the ground here, and then the Sunjammer concept is supposed to be a 38-meter. So getting to the diameters that I'm talking about is not unrealistic. And then a few other things that should be addressed is, am I out of time? All right. Is the high heating loads on the mirror. I've kind of already mentioned that. And then just doing systems design. So there are issues to be addressed, but in my opinion, they're all engineering issues. And when you look at all the operational capability that the solar collector gives you, you can imagine launching dozens of these on one heavy lift vehicle and having them float around the solar system, pushing things around and generally making things the way we want them to be. So I will shut up.
For any questions in the audience?
I've seen the movie of the solar thing, the actual test unit you have. What is the diameter? That's about 20 meters, right?
Harold?
Oh, 18 feet, so 6 meters. And that does a really nice job of vaporizing or melting or whatever things that are put, at least according to the movies I saw, at the focus there.
Right.
So
Now,
that kind of worries me about that one.
This one here?
Yeah. I've seen a movie of that thing in operation. That would kind of worry me about putting basically an optical flat there, right? Mm-hmm. Like if the reflector's over there, I have an optical flat to aim it over there.
Right.
So you have dust probably coming off the surface because you're heating up the surface. So over time, that dust is going to float over to me. It's going to coat this optical flat. It seems like, it wouldn't take much coating to sort of like make the thermal really
and there is
bad.
a survivability issue, but you also have to consider that with that level of intensity, that dust may never make it to the collector. So.
Well, meteorites probably would, and they would, put small pits in the surface.
Well, and that's fine, but we've considered that for solar sails. The sail, the pictures I've shown haven't shown all the rip stops and whatnot that you design in there, so that when you do get a puncture that it stops. It's kind of like World War II when we used to drill holes in planes so that we could stop the cracks in the aircraft.
Sure.
So-
And the mirror backing material is something very light, right?
The what?
The actual main mirror there.
Oh
not
yeah,
in that
it's usually
case, but-
Mylar with coated aluminum on the front, and then you have one of several coatings on the back that's to increase emissivity to kind of keep the temperature of the sail down.
Yeah, so that you could have little holes in or meteorites going through or
All
whatever
day.
would be fine. It seems like the flat, the secondary
secondary.
mirror is the one that would.
You're all right. What you're calling the flat is the secondary.
Yeah.
Yeah, the secondary is a critical path here. There's no two ways about it. You know, if I got 3 months operation, you know, in front of an asteroid out of one of these things, I'd be very happy. And you know, again, you know, we need to get into this facility, in my opinion, and figure out how far away we can stand off. And you know, there's the trade. If I stand off a kilometer away, I might get 50% of the radiant energy. If I stand half a kilometer, I might get 80%. And figuring out that so that we can figure out, you know, how much material is incident onto the sail. We also need to understand how what's coming off of you know, the ejector from the asteroid, how that's going to be affected by that beam. When you think about it, that secondary is kind of protecting itself. There's a beam coming off of it, and so those particles have to fight their way up that beam to get to the secondary.
Okay.
Thanks.
All right, thank you. Appreciate it.
Okay, our next talk is by Steve Chesley. Steve is an expert in asteroid and comet orbit determination with NASA's NEO program office at the Jet Propulsion Laboratory. He is presently a co-investigator on the OSIRIS-REx asteroid sample return mission. Go ahead, Steve.
Thank you, Paul. Is this working? And we're almost to the end of the day. One more talk after me. Congratulations. This is a sort of a schematic or cartoon of the concept here. AIISW, Impactor for Surface and Interior Science. What you have here in the background is the OSIRIS-REx spacecraft at the asteroid venue, which is where it's going to collect a sample and bring it back to Earth. While OSIRIS-REx is at its station after it's collected its sample, the AIISW spacecraft will come in and impact, and that's the asteroid deflection experiment, as well as a great scientific mission. So a little more detail. The AIISW is intended to launch as a secondary payload. So one of the nice things about this is it's a Don Quixote mission, some of you may know about, except that we don't have to pay for the observer spacecraft, and we don't have to pay for a launch vehicle. So it's very efficient. Indeed, it's based on an ESPA that minimizes the impact on the primary payload. After the cruise, impacts the asteroid while OSIRIS-REx is there and in a position to observe, but after it's collected its sample and safely stowed it in the sample return capsule. As I mentioned, it's going to observe the impact from a safe position, and after the debris clears, it will go in and collect spectra and imagery of the sample site, as well as measure the asteroid deflection caused by the impact. So the conclusion at the beginning here, the takeaway message is that AIISW would leverage significant NASA investments in terms of, say, the primary launch vehicle and the OSIRIS-REx spacecraft to deliver potential discovery-level science and provide a first-time demonstration of asteroid deflection. And all this is the tiny cost of a standalone mission where you have to pay for your own observer spacecraft and so on. And I think this fits well within the NASA Asteroid Initiative Grand Challenge, which talks about finding the asteroids and knowing what to do about them. This is a convergence of technology in terms of the deflection and the terminal guidance, the exploration, which here I include resource utilization and extraction. And I think the most compelling for me is the science returns from this. And let's see, so one of the program goals I'll just mention is the mitigation of potentially hazardous asteroids. I'll mention here, I'm not sure, depending on how you read the RFI for this, if the deflection or the asteroid initiative is a part of the asteroid retrieval mission concept, or the other way around. I take the view that the asteroid retrieval mission is one part of a larger program that's exemplified by the asteroid initiative. So stepping through these three things, first is the technology demonstration, the deflection demonstration. The NRC in 2010 put out an excellent report that called as a first priority for a space mission in the mitigation area is an experimental test of a kinetic impactor along with these characterization, monitoring, and verification. So this is exactly what AIISW would provide. In the area of exploration, we have these strategic knowledge gaps that have been put forward as considered to be important things to understand about these targets before we can go put humans in the environment. There's broad themes, and ISIS touches sometimes more, sometimes less, on about a dozen of these, some of these critical ideas like geotechnical properties of the small body surface, the particulate environment around the small body, and the local and global structural stability. These are the kinds of things that we want to know before we put humans into that environment. Okay, the science, I think, is maybe this is what distinguishes this approach and this particular demonstration mission from much of what we've heard so far today. ISIS is going to answer a lot of questions about what these things are made of. We're going to watch the impact happen, and we'll learn how the asteroid responds. In the local sense, we'll look at the ejecta field itself and the crater morphology, the possible release of volatiles from the impact site. On a more global sense, we'll look at the trajectory change in the asteroid, which will tell us about the interior mechanics of the body. We'll look at the rotation changes that we induce, as well as seismic activity that will be reflected through the dampening of shock waves and, say, landslides and topple boulders and so forth, because we'll re-image the entire asteroid before through the OSIRIS-REx mission and then after. So based on what we observe, we can now do some analysis to understand more about the asteroid, learning about the strength, cohesion, porosity of the impact site, as well as the geology of the subsurface. Basically, the crater will allow us to look inside the asteroid in some sense. All right, how are we going to get to the asteroid? Well, we have, as you can see, a list of ways to do it. We have been talking, and so the original incarnation of this concept was to get a ride on the InSight mission to Mars. And that's now been bypassed basically due to schedule and fiscal constraints. That this is passed. Similar, OSIRIS-REx would have been a great ride. That's also a little late. We're a little late for that. The InSight backup works, but it's unlikely to materialize. I also mentioned there's the B612 Sentinel project, which is sort of a crowdsourced, crowd-funded near-Earth asteroid survey mission. We could use that, but I think that they're past this launch date, which is the only one of theirs that worked. If anybody knows of an ELV launch to Mars in 2018, let us know, because we would like to talk to those folks. We haven't found one, but that would also work well. So as I say, there's a lot of ways to get there. At the moment, what we're looking mostly at are the possibility of a geotransfer orbit transfer through lunar flyby on our way. It works quite well, and we can get some nice impact velocities. We also have the similar opportunity to, instead of the OSIRIS-REx, or in addition to the OSIRIS-REx mission, we could go to the Hayabusa 2 target, 1999 JU3, and do the same thing and arrive at a time that's appropriate for that mission. Other things that are on the table here is the SLS test launches that have been discussed earlier. These are not ESPA compatible, so they don't look like they're a very good solution. Dedicated launch, of course, you start running into cost issues right away, and it diminishes the efficiency of this approach. So this is our main focus at the moment, is these GTO transfers. We have a notional flight system. The main point here is it's very simple. There's no new technology development. All of these things are off the shelf. You see there's the ESPA ring that imposes no impact on the host payload. A very modular flight system with the ring, the tank, a prop module, avionics module, some solar panels. Simple. There's no science instruments, no mechanisms, no deployments, pyros, no cross-link communication to the observer spacecraft. So sort of dirt simple here. The other question that comes up often is how are we going to hit this thing? And I think that's maybe a surprise to some, but we really have this problem pretty well licked with JPL AutoNav technology, which was already demonstrated on deep impact. And just retuning the targeting parameters, here's the kind of the approach. We have notionally a maneuver at 1 hour out and 30 minutes out, and a few minutes out would be the 3 targeting maneuvers. And you can see here's a 500-meter asteroid like Bennu, and we have no problem with 3 Sigma hitting very close to the center of our target. One of the reasons OSIRIS-REx is such a good candidate for this is that the timeline is suitable. So the OSIRIS-REx nominal mission has a couple of months for acquisition and rendezvous, about 9 months from rendezvous to first sampling attempt, and another 6 months of margin where they may be doing a second contingency sampling attempt, for instance. There is a possibility of a third contingency sampling attempt, but they have about over a year of slack time while they wait for their injection opportunity back to Earth. And then their return window opens here and lasts for about 4 months, and that's when we would come in just as they're getting ready to depart and do our impact and then conclude the science investigation. Here's a notional mission for a late 2017 launch that we have, a 14 kilometer per second impact with 600 kilograms. That gives you something like 19 tons of TNT released in the kinetic energy. So what OSIRIS-REx would be doing during this time frame here, after the impact, or even before the impact, we'd like to go in and get a last-minute update on the ephemeris of the asteroid, so we know what it was like before, so we have something with high fidelity to compare it with after. It'll go back and image from a safe location and monitor this ejecta as it dissipates. Then there will be the crater reconnaissance period, which would probably be a few slow flybys at low phase angle. And then the radio science to determine the deflection and global remapping of the surface to look for these changes that have been induced by the impact. So one of the first things people say, especially the OSIRIS-REx people, I'm on the OSIRIS-REx team, by the way, so I have a vested interest in that mission's success. But their first response is, you're going to do what at our asteroid? And I think if you do a careful analysis, a thoughtful consideration of the risks that are introduced to the OSIRIS-REx mission through this approach, they're not very severe. There's some additional proximity operations would be required by the OSIRIS-REx spacecraft, but these are all basic things that have been already done in the prime mission many, many times. There is a high velocity debris hazard in principle, but we know where that debris is going and we don't stand there. And that's the main way to avoid that. There's also a low velocity debris hazard. You can't go back in to survey the area until it's all been swept clean. And that happens on the period of 2 to 4 weeks. And while that's happening, you monitor and you survey the area so you know what's there and you don't go in until it's safe to do so. There was also some concern, I'll mention, that OSIRIS-REx could somehow get outside of its injection window. And I think the response to that is that you just make sure that your schedule is set up so that you go back to Earth with your precious sample when it's time to do so. And that's, this is what is considered secondary or bonus science to the OSIRIS-REx mission. The prime science, of course, is to get that sample home. Okay, so the conclusions. This is a low-cost mission concept that addresses strategic goals at NASA and provides a potential discovery class science across a number of asteroid specialties. And the mission would leverage investment in existing assets, and co-manifesting with some other launch would even further improve the cost effectiveness. I'll close by saying that near Shoemaker, which I worked on, was NASA's only NEA rendezvous mission to date. The next one is going to be OSIRIS-REx, fully a generation later. And so I think this opportunity represents a one-in-generation chance to have a low-cost asteroid impact deflection. And what I'll say in the context of the ARM program is that this obviously can be redone with other missions. Like I mentioned, Hayabusa 2. If you're going to, say, pick up a rock at a larger asteroid, After you've gotten your rock and you're backed off to a safe position, then you can have your impactor spacecraft come in, and that asteroid retrieval vehicle could return, survey the impact site, and you go ahead and measure the deflection that was induced, and so forth. So I'll stop there. Thanks.
Thank you. Do we have any questions for Steve? Go ahead.
Yes, I'd like to ask about the size of the spacecraft. You know, there are many GTO launches, about 20 a year, so there certainly are a lot of those, although not a lot of them are not Atlas. Did you consider a smaller vehicle for two reasons? One is it might be able to be launched on more GTO launches on various launch vehicles. The other, if you're going to use that technique, so if you could work with a smaller vehicle, you'd have more flexibility there. But you'd also would gain something if you had a smaller vehicle when you did the impact, because it would be, you would still be, I suppose it would still be a scientifically interesting impact, but there might be less debris thrown out to worry people with their OSIRIS-REx or their other spacecraft that's there.
One of the key objectives here is to produce a measurable deflection. That's both for the planetary defense aspect as well as the scientific aspect. And this concept, as I showed you, I didn't mention, that's about 1/10 of a millimeter per second, which allows us to detect the deflection with about SNR 10 after several weeks of observing. If we get smaller than that, we're going to start to lose the ability to make that detection. In terms of GTO launches, one of the options that's always available if you're trying to get a ride is to upgrade the launcher to provide enough throw to get your spacecraft along with the primary payload.
Steve, I've been hearing that SpaceX is looking for a payload for its first deep space test of the Falcon 9 Heavy. Have you talked to them?
No, I haven't. If they're looking for a payload, we would probably be able to stack about 18 of these things in the Falcon 9 Heavy, so that could be okay too. Maybe we should do that.
One really quick comment, and then we have to move on. One real quick.
So I just have to ask, are you going to be sending the video back to Earth?
The OSIRIS-REx spacecraft will be there. It'll have the best view. There won't be any images returned from the spacecraft.
But you'll have a camera, right, for targeting?
Yeah, with not very good data delivery. That's not the objective. We already know what this thing looks like, and the asteroid, and we'll have the best view from the OSIRIS-REx spacecraft. We won't get the data back unless we miss.
All right. Thanks, Steve.
Okay, so we're at the last presentation for the day, and the presenter will be joining us virtually. Jonathan Werbel is a senior research scientist in the Flight Systems Group at Honeybee Robotics, where he supports R&D efforts in sensors and integration systems. Can you hear us, Jonathan?
So he can't hear me. He's going to start presenting.
Okay, he can't hear us, but
He's moving from the phone.
okay. We'll be,
I just let him know he's going to start.
okay, all right, go ahead.
Yep, I can hear you guys. Can you hear me?
Yep.
Usually,
Can you guys hear me?
I got him. Good.
Okay. Looks like I just got confirmation over the IM. All right. So, yeah, thank you for the introduction. Today I'll be presenting on Honeybee Robotics technologies that can support deflection demonstration. As I'm presenting remotely, please let me know if the audio is coming through clearly, and during my talk, please relay any questions or interjections through the IM window, as I'll have my audio off to reduce echo. All right. So, to begin, I'd like to provide a bit of background on Honeybee Robotics. Founded in 1983 by Steve Gorvin and Chris Chapman, Honeybee Robotics Spacecraft Mechanisms Corporation is a privately owned small business committed to developing high-reliability mechanical and electromechanical products for the U.S. government, as well as for the private aerospace and space sectors. Honeybee Robotics has offices in Pasadena, California, Longmont, Colorado, and our headquarters in New York. We're celebrating 30 years of developing space systems. This has included involvement in a number of NASA missions. We developed the rock abrasion tools for the 2003 Mars exploration rovers, 2007 Mars Phoenix lander, the TEGA, dust cover and icy soil acquisition device, 2011 Mars Science Laboratory. We delivered the robotic sample manipulation system and the dust removal tool end effector. So we currently have 6 gadgets on Mars and have successfully completed over 300 excavations on the Martian surface. We believe this work is helping pave the way for human exploration of Mars, and we're open to support both robotic and human exploration of asteroids, as well as deflection of asteroids if the opportunity arises. Let's see, next slide. At this workshop, Honeybee Robotics is presenting in a number of topic areas, including Topic 2, the asteroid redirection systems, and Topic 3, asteroid deflection demonstration, Topic 4, asteroid capture systems, and Topic 5, crew systems for asteroid exploration. And we also presented briefly on Topic 6, partnerships. I'm going to briefly touch on some of these technologies in the other topic areas, as there's overlap in their applications, but I'll focus on their application to Topic 3 for this session, asteroid deflection demonstration. So the way we see our technologies, they enable us to interact with the asteroid in different ways, from helping us to, if you will, better see it, touch it, anchor to it, etc. Many of the technologies I'll present have their primary utility in deflection missions seeking to make physical contact with the asteroid. So please bear that in mind. Regarding the ability to see it, Honeybee's developed laser-induced breakdown spectroscopy, LIBS, instrumentation, as well as 3D LiDAR. The former enables acquisition of composition information prior to engaging the asteroid, and then the latter supports proximity operations. LIBS works by using a liquid vaporized and ionized surface material, and when that plasma puff cools and recombines, it emits a spectrum representative of its composition. This allows identification of surface materials without having to collect them. And by adapting LIBS to a standoff LIBS version, which is laser-induced breakdown spectroscopy done at a long range, the spacecraft can better characterize the asteroid before interacting with it. The 3D LiDAR vision system acts much like the human vision, with its small area of high resolution surrounded by a large area of low resolution for spatial context. This will help for proximity operations if the mission includes interfacing with the asteroid surface and touching down on a suitable landing site. Alternatively, we can impact it, and impactor technology will be useful prior to engagement with asteroids. This has been discussed throughout the conference or workshop. For spectroscopy and other surface analysis, those can provide information about the material composition, but be difficult to determine the structural strength of the asteroid, which is very important with physical contact being planned or for an larger impact or deflection. The physical properties of the asteroid are poorly understood, are likely poorly understood, and could range in strength from highly competent basalt to weak, loose rubble. So the C-Cross impactor shown left allows sighting the composition of the asteroid from a distance. It utilizes a probe launched from an orbiting spacecraft to impact the surface and collect scientific data, measuring the forces at and after impact to gain knowledge about the asteroid's physical properties. This technology leverages from a similar mission that has demonstrated success, the LaCrosse, the Lunar Crater Observation and Sensing Satellite Lunar Reactor Probe, which was launched from the LRO Lunar Reconnaissance Orbiter spacecraft and successfully gathered data about the moon. A C-Cross probe is a small instrumented sphere, like less than 20 kilograms, designed to impact a comet or asteroid at about 10 meters per second and measure the forces at and after impact with a high degree of accuracy. So alternatively to impacting it, we could just touch it. And here the touch and go surface sampler, which is shown first figure, was developed by Honeybee Robotics to drill and acquire a sample of regolith up to about 50 cc's of weak consolidated materials with a unconfined compressive strength of less than about 10 megapascals, while the cutters penetrate to a depth of 1 to 4 centimeters. Again, this is a useful capability if physical contact is planned for deflection. physical properties of asteroids, again, will likely be poorly understood and could range from loose to well consolidated. The system is reusable and can store samples inside individual containers for in situ analysis or sample return if the time permits. The touch-and-go surface sampler consists of a high-speed sampling head attached to the end of a flexible shaft, as shown in the second figure. The sampling head rotates its counter-rotating cutters at a speed of 5,000 to 8,000 RPM and consumes about 30 watts of power. The mass of the current prototype is around 450 grams with a volumetric envelope of 50 millimeters by 75 millimeters by 150 millimeters, excluding the drill. A prototype was developed and tested in a laboratory ambient environment on various target materials. The TGSS was demonstrated to sample regolith at a rate of 30 cc's per second and consolidated chalk with strength of 10 megapascals at a rate of about half a cc per second. A number of microgravity tests have shown that the TGSS can sample both consolidated and unconsolidated materials and includes a sample canister change-out system that allows sampling of multiple sites with minimal cross-contamination, if desired. In addition, you can harpoon sample surface. It's another technology worked on for robotic sample acquisition for the surface of an asteroid, and it's the AR probe, which would bring a sample back to an orbiting spacecraft, providing composition information before the parent craft engages the asteroid. This harpoon and drilling technology leads us into one of Honeybee's strengths, and that is robotic drilling. Let's see, next slide. Drilling is often the method of choice for penetrating hard rock, and this may be of interest to anchoring an asteroid redirection spacecraft. In the vast majority of applications, drilling employs the turning of a hardened bit, which requires a certain amount of downforce, typically referred to as weight on bit. In a low-gravity environment, weight on bit can be severely limited and must be provided either by spacecraft thrusters or an anchored base for the drill to push, or rather pull against. Rotary percussive drilling action can be employed to circumvent the need for prohibitively high weight on bit. Now, the feasibility of drilling into small bodies with low weight on bit has been demonstrated, and I talked about this in an earlier talk, so if anybody's joined me from there, please bear with me. And it's been done using relevant analog stand-ins for likely asteroid surface materials. Such testing demonstrates that the feasibility of drilling into a small body with low weight on bit is dependent upon the strength of the materials comprising the small body. Drilling in low-strength materials such as plaster or limestone is feasible using a commercially available drill with a 1.6 millimeter diameter bit and as little as 5 newtons weight on bit. Plaster and limestone have a unconfined compressive strength of about 8 megapascals and 40 megapascals respectively, which should be representative of a C-type asteroid. However, higher strength materials such as those of an S-type asteroid cannot be drilled as readily with that low downforce. So for instance, a 120 megapascal basalt is representative of the upper rim of an S-type asteroid materials and cannot be penetrated with that low weight on bit. It's not to say you can't do it, but you want to test it and ahead of time and have contingencies if what you wind up with on site is not what you expected. Now the next thing is we can inhale it and and spit it out, and I'll get to that. While we're not proposing to vacuum the asteroid out of existence, this technology is presented as part of the cruise systems and may provide utility for a deflection demonstration. As mentioned in a talk on utilization of surface materials for asteroid deflection, it may be possible to use the asteroid bulk material as a reaction mass. This system supports collection of loose material, which can be fed into a mass accelerator. So shown on the left, we rely on injecting pressurized gas into the top few centimeters of regolith, and then capture the regolith propelled upwards by the escaping gas into a transfer tube. The pneumatic approach can be used and is ideally suited to obtaining both small samples for scientific analysis as well as bulk sample for mining and processing of resources. Gas could be supplied by electrolyzing water and oxygen. For bulk regolith mining, a potential approach might be to use a system that has been initially developed for lunar regolith mining. The pneumatic regolith miner is simulated is similar to a conventional vacuum cleaner. However, instead of creating suction at the nozzle mouth, a compressed gas is injected, moving the captured soil with it within the nozzle up the tube and through the cyclone separator into a soil bin. Shown right is the pneumatic excavator integrated into the NASA Ames Center K-10 mini platform. The system has been successfully tested in a 3-meter-long bed filled with G1 soil simulant within a 3.5-meter vacuum chamber. Now, in addition to inhaling it and sitting it out as a way to deflect the asteroid, we can also lasso it. Honeybee has done work in grappling a spacecraft in orbit, and our lasso technology can be used either to anchor to protrusions on the surface that are part of the larger boulder or asteroid itself, much like slinging a horn when rock climbing. In this case, the technology could be used for spacecraft anchoring and transfer forces and torques to the asteroid itself. Shown above is basically a lasso, hence its namesake, and it's cinching down on an expansion nozzle and then picking it up in 1G. A fairly simple concept, but if the asteroid is expected to present itself with the opportunity, it could be fairly effective. We can also anchor to it. Now, Honeybee Robotics has a number of technologies that support the ability of spacecraft to anchor to the surface. In this microgravity environment, anchoring of equipment is crucial, allowing it to subsequently apply weight on bit for drilling or lateral forces for D-spin, depending on the conouts. Honeybee has a long history in anchoring and has developed a number of approaches, including hard rock drilling and hammering for setting anchors, with preliminary feasibility tests yielding positive results. Now, testing was performed with a 3.8 millimeter nail, a traditional hammer, as well as an off-the-shelf nail gun, and that was into 8 megapascal plaster, 40 megapascal limestone, and 120 megapascal basalt. As you'd expect, the nail only penetrated the blast successfully, while the other two it failed, but the nail gun, on the other hand, was powerful enough to drive a short nail into all 3 rock types. So this type of research has shown that you might be able to anchor fairly quickly to the surface of the asteroid, and it was made possible by Honeybee's test facilities out in Pasadena, where we have a large library of rock samples allowing tests of drills and anchoring schemes. Now, Honeybee has also worked on fluid anchors, and that allows anchoring to featured surfaces, with the benefit that the anchor deployment does not exert any force that would require reaction by the spacecraft. In the fluid anchor approach, a wetting fluid such as foam, cement, epoxy, etc., is injected onto a surface or into a hollow spike on the footpad, and if applied to the surface, the goal of the fluid is simply to fluid anchor is simply to inject an adhesive cushion between the rock and the pad, the ground pad. Otherwise, if it's injected into the ground, the fluid would go deeper into the loose gravel or soil, allowing the anchor to engage a larger volume of asteroid material, forming a composite footing glue mixed with the soil. Now, the self-opposing multi-mode anchor shown in this slide allows payloads and equipment to be securely anchored to the surface with minimal applied force by laterally opposing the angled anchors. So there's a number of ways that we feel we can anchor to the surface of an asteroid in order to transmit forces and torques to it. So, in conclusion, I've presented a number of technologies that can support an asteroid redirection deflection demonstration, principally involving physical contact with the asteroid. Now I'd like to open it for questions, and also I encourage you to visit our website. It's at the bottom of the page to further explore our technologies.
All right, thank you, Jonathan. I'm not sure what the delay is here with questions, but are there...
10 seconds.
Okay, about 10 seconds. Does anybody have a question for Jonathan? Are there any online? Yeah, basically, Jonathan, we don't have any questions here, and we appreciate your participation and the information. I think there's some applicability of these different types of devices for potential demonstration, either as part of a planetary defense or potentially just as a prototype. So thanks very much. So, I know it's late. but we've got about 20 minutes before we wrap up the session today. And what
You're
I'd
welcome.
like to
Thank
do
you.
is open the floor up for comments, particularly if folks are not going to be here in the morning. Make sure that if you've got something that you want to convey and discuss. I have a few ideas or conversation starters for this afternoon, but open it up to the floor or anybody online. So, okay. Quiet, okay. I guess I'll start out I think there's the goal of what we want to provide here is some findings and recommendations from this session about out of the workshop for areas that we think as a group should go forward as for further study, for example. It basically goes, I think, into a couple classes of different approaches. One is the direct demonstration of a planetary defense technique, and that kind of breaks down into the least cost complexity, where we're basically, for the ARM mission, we're utilizing things that we already have, that we're not adding anything to the mission. And then we've got these additional aspects of things that we can show, understanding that there's likely an incremental cost unless it's provided in a cost-sharing type of an arrangement. And then there's a third class of experiments, demonstrations that probably aren't applicable directly to this ARM mission, but could be very applicable to planetary defense in general. The one that comes to mind is the nuclear detonation. In any of the approaches that we've looked at so far, we don't want to do anything with respect to nuclear because of the obvious cost and schedule and other implications. However, there may be the opportunity in combination. I'll give an example. The kinetic impactor approach, very similar to OSIRIS-REx and ISIS, could be repeated for example, for the alternate approach of going to a large target. If we go to the reference approach, it's really not a player because you definitely don't want to be impacting the thing that you would bring back. But as part of that kinetic impactor, Bongwi's hypervelocity impactor, you could at least test potentially a mechanism on that, for example, for the boom that would have a dummy payload. So you could test out the approach. It wouldn't be a demonstration of the actual capability, but at least a demonstration of the approach that you would use. So in the first category that we've talked about, of actually a technique that could be implemented on the retrieval mission, or the redirect mission, I think for both approaches, whether we go to a small one or pick up part of a large one, is I think the gravity tractor, the ion beam shepherding or ion beam deflection are certainly both that I think are applicable there. And I think they need to be looked at a little bit more in depth to see how effective they are, and then what are the pros and cons of each approach. In the alternate approach that we've been looking at, we've been focused on the gravity tractor with the enhanced mass augmentation. But that's not because we're getting a boulder, because we're already going down to the surface as part of the nominal mission. So the risk there is somewhat minimal, incremental risk, but certainly the ion beam deflection approach could be tested too in that manner. So I guess, try to get everybody's comments, or if there's any additional feedback on that. I have some specific questions for the presenters that I might be able to talk about. And I'll turn it over to Paul to see if he has some comments.
So one of the things I thought that we heard some very interesting ideas. One of the concepts that was novel, I think, or not novel, but is a little bit of interest that is applicable directly to ARM, of course, is the ion beam. I think that's something that is people haven't thought as much about. I think we've thought a little bit about the gravity tractor. It'd be interesting to see what the boulder option has in terms of the enhancement, but it would also be interesting to explore the aspects of the ion beam system and what that does to your target, to your asteroid. One of the things that would be interesting to see is what effects do you have on the surface, especially if you're talking about coherent versus robopollination and things like that. Maybe there are no effects, might be minimal, but it'd be interesting to at least explore that. So there's what I see out of this, especially because of its relevant for ARM, is the trade between, what type of demonstrations can you do effectively, given the time that we have, the budgets that we have, and the constraints we have. It would be great to include all of the type of deflection techniques that we might use. So, for example, could you test a ion beam? Could you test a gravity tractor? And at the end of the mission, when you have your sample, you have your whatever it is, especially if you're going to a larger target, can you do a deflection demonstration with a kinetic impactor, a la AIISW after the end? That would be sort of, my wish list. If I was, king of the world and be able to do that, that would be the greatest thing to do. Again, we have to keep in mind the constraints that we're under. So that's what I'm interested in. I would be interested in getting other people's feedback on what type of things they would like to see. Again, this is a idea synthesis. We'd like to try and get some feedback from the community and see what we have. So, come on to the microphone, and then we'll go from there.
So go ahead, Andy.
Okay, I'll go first. Well, one thing I think is important is that we can combine these techniques, and I think we don't want to just have one compete against the other necessarily, but to see if there's a combination. It occurs to me the ion beam concept might benefit, for example, from wallpapering the asteroid first. You could bring along your own folded up surface that you put on the asteroid that you're going to put the ion beam into. Since we're going to be ruining the surface for scientific value anyway with the ion beam, probably wallpapering won't make it any worse. So that's kind of the equivalent of pick up a rock for ion beam, is some sort of previous preparation of the asteroid to receive the ion beam. For one thing, if you wallpapered it, what you could do is make it as a perfectly round piece of wallpaper that maybe hangs off the side a little bit, but is anchored somehow so that you now have a bigger target to shoot into and a better shaped one.
Yeah, Andy, just a comment with that. The problem that you encounter is because of the rotation of it, you can't just pick one spot unless you only want to demonstrate at very discrete points. So,
can I respond to that? Well,
sure.
Maybe what you do is you wallpaper it all the way around.
Okay.
And you sort of do the sort of wallpapering job I'd probably do if I tried wallpapering anything. Where I'd make it nice and round and pretty, but it wouldn't be. My wife would tell me that it's got to be re-wallpapered because it's not lying as flat as it should.
The comment I have is it might take a lot of wallpaper, and trying to do that maybe the complexity and the extra cost and mass and things like that. So it's something we'll think about, but that might be problematic to do that. So
listening to all of this, it seems to me you're going to be forced by events likely. I have a feeling that you're going to find that, when you get ready to fly the mission, there's only going to be one or two candidates. There's not going to be pick from 10 sort of. So it's whether you do pick up a rock or bring the whole thing back will be dependent on what's available when you want to fly.
Right.
And then that will determine what sort of deflection mission you do. If it's pick up a rock, you can do the ion thing. If it's bring the whole thing back, you're going to have to do the gravity tractor because you don't want to ruin the surface with the ion. So I just have a feeling that'll be forced by events.
Yeah. Well, certainly the type of target that is available may force you down a path of a certain type of technique, but I think from our point of view, it'd be nice, especially because we're talking about asteroid deflection, to try and at least test multiple techniques. But you're right that it will be somewhat target dependent in terms of what's available. In terms of what are if we go to the bigger targets, removing a boulder, or actually finding some of these smaller ones to go after and returning the whole thing. So your point is well taken. I think what we're trying to do is see what we can maximize the knowledge that we have for multiple aspects of asteroid deflection.
So there's a lot of things you could do if you integrated all these ideas. You could take and see every Falcon Heavy that's leaving and see its upper stage as a resource, because you're going to get to the same delta V that the payload is going to get to with that. So you might as well just stick with it like you do with ISIS or L-Cross, and use that mass as part of impact the velocity. So anyway, you could put an EP system into the ESPA-based vehicle that would be a secondary, and send that to the asteroid to do the gravity tracking. Other things that you could do is, nobody mentioned solar sailing. We had the solar concentrator, but that concentrator, if it's attached to the vehicle, could be a great solar sail, and that would impact it. And you could attach it, and it would, over a certain period of time, it would take out all of the rotation, because, if it's pushed back, basically becomes like the feathers on an arrow. And then if it has enough frontal area still, then it will alter the asteroid, trajectory. And that would be almost a passive system. You just have to get there and, attach it. And anchor it, just anchor it. And so you could couple that in with an active demonstration. After the active demonstration has exhausted its propellant, then this piece of it would continue on. And you could use the Falcon Heavy's upper stage as sort of your mass to get it there, and help, rather than having to extract a rock from it, it's already at the necessary delta V. So there's a lot of ways you can creatively integrate a number of elements and try to use free things, or at least very low cost things.
Yeah, no, I think that's a good comment. I think one of the things that, and this is kind of a question to the solar collector side of things, but it goes to the solar sail too. I think one of the reasons why it probably has not been discussed much is the low TRL that's associated with it. We have flown, there are some that have flown, but there's at least a perception that it's fairly low TRL. So maybe I'll let, real quick, Rob respond to that.
Well, but we've seen several solar sails fly. We've got the Icarus mission that the Japanese did. We've got Nanos LD, and then we've got the TDM mission that should fly next year. So there's been a lot of progress in this area, and I don't see it being any more development than a lot of the things that we're talking about with capture mechanisms, or really kinetic deflectors. We've done a lot of work on that, and that has a lot. And I don't see it as being any lower TRL than any of the other technologies. I've wondered why.
For a pure solar sail. With respect to turning it into a solar collector.
Yeah, I just don't see that as being that difficult. I think there's this perception that we have to have a pristine mirror because we're used to that on the astrodynamics community and whatnot. But astrophysics, I should say. But we don't need a perfect image of the sun. We need a hot spot to burn regolith. So I just don't see this being that difficult. And with the recent accomplishments in inflatables and in sails, I think those are directly applicable.
Yeah, so that goes to another question actually that I have for you, and then we'll go to you, Rob. Is that right now for the reference approach, there's an inflatable strut and bag concept, but the inflatable is only used for a very brief period of time. It's stowed, it's deployed upon approach to the target,
right.
It's captured, and then it's allowed to deflate. I think one of the concerns with inflatables is their longevity and their tolerance to micrometeoroids and maintaining that. So I think that's something to think about?
Well, actually, we've addressed that. I didn't go into it in the presentation, but we used a special material that when
Rigidizing.
you know, when it's exposed to nitrogen, and you know that's what we use there. And also, you got to think that our inflatable tubes, if you will, are considerably smaller compared to the rest of the vehicle than with these other concepts as well. So,
Right.
and this thing rigidizes in a matter of hours. So, yeah, it's something that should be tested. But I mean, it's been used before. So,
Okay.
There are ground versions of the Astromesh that have never flown that could be had for not full price.
Okay.
sounds like we're
Rob, did you have a comment over there?
Yeah, I don't know how you're planning on reporting out, but I think it would be important to bin these ideas into an asteroid initiative bin and a grand challenge bin, because what I'm hearing is, oh, that's too low TRL, and it's not applicable to the asteroid mission, and I'm afraid a lot of good concepts that might be the greater value in the long run will not get accepted at this workshop because of the myopic nature of our society. So if we bear in mind that the grand challenge is really what the president has asked us to do, and the asteroid initiative is just a component of the grand challenge, like I think was mentioned earlier, then that with that kind of a thinking mindset, I think we'll get more out of this workshop than if we just dump all the further out concepts and don't document them.
Yeah, no, I agree, Rob. I mean, look, the RFI call specifically was for the ARV, but your point's well taken. That
When I go to the opening ceremonies, it's the grand challenge that's rolled out, not just the asteroid initiative. So the message I'm getting is that the grand challenge is what we're pursuing, and the asteroid initiative is just a component of the grand challenge.
well, it's actually the other way around. The asteroid initiative is
That's what I'm
combined
asking.
grand challenge with the asteroid redirect mission. So,
Well, it's not clear to me, and I work for NASA, so I'm sure the public's very confused.
sure, but no, your point's well taken. That we don't want to, even if some of these ideas don't have applicability because they're a little bit farther term TRL, that we should make sure they're still captured, and it may be something that needs to be funded. Thanks. Fong Wei?
So I just want to emphasize that everybody feel that, oh, we have all the technology even for the kinetic impactor because we had such a successful deep impact mission. But as all of you know that this target size was what?
6 kilometers.
Yeah.
6 kilometer.
Right.
So we have to worry about hitting 50 meter, 100 meter, 200 meter. So I know JPL may claim that, oh, we can easily hit 50 meter, 100 meter, but I may suggest that next logical flight testing will be actually being able to hit 50 meter small size target.
Yeah, I don't know that we have to get down to the 50 meters.
I know, but that's the smallest target we have to worry about.
Yeah. Yeah.
No, but I'm not saying 50 meter.
Right.
But
Yeah. For
can we hit the 300 meter target?
Yeah, for example, so we may not need to take the technology demonstration all the way down to 50 meters.
Right.
But if we go from 6 kilometers
Yeah,
down
I will not
to-
choose the 50 meter because 99% we will fail.
Right. So that's something that has to be looked at as to what is the target range, and I don't know if Tim and Steve can.
Well, I
comment
mean,
on that.
a 600-meter asteroid like what Steve was talking about would be a great target, and we're confident we could hit it. But, you know, we should prove it, I guess.
Right, but I guess what's the limit?
The other thing is, for instance, for the AIISW concept, if you have an observer spacecraft and you know from telemetry what
Right.
you are aiming for,
Yeah.
and you know from the observations what you hit, so that's a demonstration of whatever level you've designed the system to be. Now, you can get, as we know from SDI, for instance, you can get meter scale accuracy if that's what you want to pay for. But as in the case of Deep Impact, which was tuned for the target that it had to hit, ISIS is tuned for the target it has to hit, and that's what we do as engineers. So, but we'll know what we hit from the demonstration.
Good.
Actually, one of the-
Probably got a minute more that we can go tonight, and then we'll probably need to adjourn here.
Just one quick comment. There's been some question about how well you could know when you hit something. And, you know, I was originally an OD guy, so, you know, it is very precise. And a useful number would be that if you can stick around long enough to see 50 meters of displacement from where it was going to be, that's easily detectable, and 10 meters is probably detectable. And so, you know, I mean, 50 meters in a month is a vanishingly small, you know, delta V. So it's a very, very small amount that you need. And so, you know, this business that you need to see a large deflection is not right. Don't get that out of your minds. If it's just a matter of, did we move it a little bit, we can see, you know, next to nothing. Okay. That's assuming you got somebody there watching. Now, if you don't, that's a different matter.
Right, sure.
Real quick, Bob.
Okay.
Real quick. I want to echo Bong's comments about the kinetic deflection. You know, we're talking about low TRL. I really think all our concepts are relatively low. When we worked kinetic deflection and we told them what delta Vs that we were looking for to actually deflect something, which is different than, you know, a demonstration mission, and they can go slower. But the closure rates, I mean, when you think about it, the closure rates, if you got a closure rate of 10 kilometers a second, 1 second before you hit, you're 10 kilometers away. So when I talked to the global missile defense folks about the closure rates we were talking about, their eyebrows went up. And, you know, they're doing a pretty hard mission themselves. Right. So, you know, these aren't easy things. So,
yeah, that's something that has to be studied in greater detail. So what I'd like, first of all, I'd like to thank everybody for their participation today. And we will be reconvening at 8 o'clock in the morning. Gives everyone a chance maybe to think about the day's events. I will be pulling together some charts that we'll use for the plenary session, and we'll kind of go over those and further address further comments. And I'll try to take into account everybody's discussion today and the comments that we've had in this synthesis period. So again, 8 o'clock tomorrow, across the way, and hopefully folks can be there and participate further. So again, thank you for your participation and have a great evening.